Section 4.6, Directional Derivatives and the Gradient. Directional derivatives. We start with the graph of the surface of the equation z equals f of x comma y. Given the point AB in the domain of f, we choose our direction to travel from a point. We measure the direction using the angle theta, which measured counterclockwise in the xy plane, starting at 0 from the positive axis. The distance we travel is h, and the direction we travel is given by the unit vector u equals cosine theta I plus sine theta j. Therefore, the z-coordinate is a second point on the graph given by z equals a plus h of cosine theta, comma b plus h of sine theta. And here we have a picture of the steady figure at a point with some angle theta. Now, throughout this section, it'll be helpful to keep in mind what is a derivative. Well, it is the rate of change. So we're going to be working on is the rate of change, the steepness along a curve at a given area, a given space in it. First definition, directional derivatives. Suppose z equals f of x comma y is a function of two variables with domain of D. Let a and b contained in D and define u equals cosine theta I plus sine theta j. Then the directional derivative of f in the direction of u is given by the directional derivative of f comma b equals the limit as h is approaching 0 of f of a plus h cosine theta, comma b plus h sine theta minus f of a divided by h. So this is, again, and I think if you just think about it from your single variable courses, it all kind of just ties better. This is just your limit definition, right, for a derivative. Where we have your function plus h minus your function. So that same idea still applies. And just like your first calculus courses, we have that definition. Our first example has us practicing our definition. It is very lengthy and I don't recommend it. So don't recommend the use of the limit definition above. Continue on to the next theorem. So we'll do the same problem twice. So if you notice example 1, example 2 are the exact same question, just different process. If you'd like to, if you have a good 10, 15 minutes to spare, you can use that limit definition for example 1. But we can do better. We can be more productive. So theorem 4.12, directional derivatives of a function of two variables. Let z equal f of x comma y be a function of two variables x and y, and assume that f of x and f of y, or actually that's not f of, the partial derivative of x and the partial derivative of y exist. Then the directional derivative f on the function of u equals cosine theta I plus sine theta j is given by the directional derivative. That's what that d sub uf means. Directional derivative of function f of x comma y is equal to the partial derivative of x comma y cosine theta plus the partial derivative of fy of f of x comma y sine theta. Let's look at this example. Let theta equal arc cosine of 3 over 5. Find the directional derivative of f of x comma y equals x squared minus xy plus 3y squared in the direction of u equals cosine theta I plus sine theta j. What is the directional derivative of f of negative 1 comma 2? Okay, so piece of information is given. We're given that theta equals arc cosine of 3 over 5, and that gives us cosine, right? Now, I emphasize that trig because I know you only get a small sample of it in your pre-cal. So um, if I have theta equals arc cosine of 3 over 5, then that means that cosine theta is 3 over 5. So we have cosine theta. And by the use of our trig identities, we can use sine theta is equal to the square root of 1 minus 3 over 5 squared. So this means that I have 16 over 25, which gives us 4 over 5. So sine theta is 4 over 5. And this right here is just an identity. I think this is one of your double angle identities from trig, if I'm not mixing it with something else. Or there's different ways to go about it. You can always draw the the sides and build your Pythagorean, your right angle, use Pythagorean theorem to find sine. Okay, so we found those angles we're working with. And then we just lightly highlight them. So I have sine and cosine. Okay. Now next, I want to find my partial derivatives in terms of x and y. Okay, so I have my function. Let's go ahead and take those partial derivatives. So partial derivative in terms of x is 2x minus y, and that partial derivative in terms of y is negative x plus 6y. Okay, now we want to use that directional derivative. So the directional derivative of f of x comma y is given by the definition. It's the partial derivative of x cosine theta plus the partial derivative of y sine theta, right? Just as we have right above. Okay, now we have all the pieces. So that we have 2x minus y times cosine theta. Cosine theta we said was 3 over 5 plus negative x plus sine theta, 4 over 5. So we just distribute these values, and our answer is 2x plus 21y over 5. All right, last piece, and I'm running out of space. Last piece of this problem, we're asked to calculate that value at point, the directional derivative of negative 1 comma 2. So we just plug in those values. So we're left to calculate. So we let x equal negative 1 and y equal 2. So the directional derivative at negative 1 comma 2 is equal to 2 times negative 1 plus 21 times 2 over 5. And our answer is 8. So I hope that made sense. And it's easy to apply that theorem for directional derivatives. The gradient. So the gradient is that change of rate along, for example, hills or waves. Let's read that definition of gradient. Let C equal f of x comma y be a function x and y such that the partial derivative of x and the partial derivative of y exists. The vector del f of x comma y is called the gradient of f and is defined as del of f of x comma y is equal to partial derivative of x comma y I plus the partial derivative of y of x comma y j. the vector del f of x comma y is also written as grad f. So we have a new notation. So we have like this upside down triangle. It's actually called a nabla, and that's what the sign's called. And it's read as del f. So you can read del f, or you can just say the gradient of f. For us, we can say also the gradient of f. Nabla. Okay, example 3. Find the gradient of f of x comma y of each of the following functions. So we have f of x comma y equals x squared minus xy plus 3y squared. Okay, so this is pretty straightforward. What is our definition above saying? It says we take our partial derivatives, right? And we write them as I and j. And there we have it. So let's go ahead and do that. Let's take our partial derivatives. So f of x, or partial derivative of function f in terms of x, is 2x minus y. So I look at them, I take the derivative of x's. Your y's are constants. Okay, now for my partial derivative in terms of y, I look at my function and I take the derivative of y. So an x is a constant, so I don't worry about that one. Here, the derivative of y is 1, so I'm left with negative x. The derivative of y is 6y plus 6y. Okay, now we want to write it. So our answer would be, yeah, you can see the definition right there. So the gradient of f of x comma y is defined by 2x minus yi, which is our function f, plus negative x plus 6yj, which is our partial derivative for y. Let's go on to the next one. So we have some chain rule. Let's go ahead and begin with the partial derivatives. So same as above. Partial derivative in terms of x is 3 cosine 3x times cosine 3y. Partial derivative in terms of y is negative 3 sine 3x sine 3y. Alright, so therefore our gradient of our function, or our del f, is 3 cosine 3x cosine 3y I plus 3 sine 3x sine 3y j. Okay, so include this text from your book. The gradient has some important properties. We have seen one formula that uses a gradient, the formula for the directional derivative. Recall the dot product, that if the angle between two vectors a and b is phi, then a dot product b equals the magnitude of a times the magnitude of b cosine phi. Therefore, the angle between del f of x naught comma y naught and u equals cosine theta I plus sine theta j is phi. We have the directional derivative of f of x naught comma y naught equals del of f of x naught comma y naught dot u. equal to the magnitude of del f of x naught y naught times magnitude of u cosine phi equals the magnitude of del f of x naught comma y naught cosine phi. The magnitude appears because u is a unit vector. Therefore, the directional derivative is equal to the magnitude of the gradient evaluated at the point x naught comma y naught multiplied by cosine phi. Recall that cosine phi ranges from -1 to 1. If phi equals 0, then cosine phi equals 1, and del of x naught comma y naught and u both point the same direction. If phi equals pi, then cosine phi equals -1, and del f of x naught comma y naught and u point in opposite directions. In the first case, the value of the directional derivative f of x comma y is maximized. Second case, the value of the directional derivative of x comma y is minimized. If the gradient of x comma y equals 0, then the partial derivative of x comma y equals the gradient of x comma y dot product u equals 0 for any vector u. These three cases are outlined in the following theorem. So you can just summarize them here. I know it was notation heavy. I guess now that I'm here, I would suggest you kind of ignore it since it is a lot to process. Theorem 4.13, properties of the gradient. Suppose the function z equals f of xy is differentiable at x comma y, and we use not to show that those little sub-zero notation to show that's a specific given point. So first, if the gradient is 0, then the partial derivative is 0. Second, if the gradient is not 0, then the partial derivative is maximized when u points the same direction as the gradient. 3, if the gradient does not equal 0, then the partial derivative is minimized when u points the opposite direction. Okay, so this is a picture that kind of shows the movement of these vectors. Now, it's kind of weird. The best summary I can think of is think of these as changing slopes along a hill. They're just slopes. And in a weird sense, they're kind of perspectives along slopes. Let's do example 4. Find the direction for which the directional derivative f of x comma y equals 3x squared minus 4xy plus 2y squared at -2 comma 3 is a maximum. What is the minimum value? All right, so let's begin by finding those partial derivatives. Okay, so we have the partial derivative in terms of x, which is 6x minus 4y, and our partial derivative in terms of y is -4x plus 4y. Now we have our gradient, our del f, given by 6x minus 4y I plus -4x plus 4y j. Now, to evaluate the gradient, we have del f is equal, or del f, we're given the point -2, 3, is equal to 6, -2 minus 4 times 3, I plus -4 times -2 plus 4 times 3j, and that gives us -24i plus 20j. Okay, now we want to find the direction of it, right? So we want del f divided by the magnitude of del f. Luckily, we have these pieces here. We have negative 24 and 20. So we can begin by we can just find it in one shot, right? So we have negative 24i plus 20j. In the denominator, I have negative 24 squared plus 20 squared under a radical. So this right here gives us 4 square root of 61. So we're left with 24 over 4 square root of 61i plus 20 over 4 square root of 61j. And we can go ahead and simplify those numerators, right? So we can get a 6. But then we have to go ahead and simplify or rationalize those denominators so that we have, that was always a negative, negative 6 square root of 61 over 61i plus 5 square root of 61 over 61j. Now, to answer the question, what is the max value of the directional derivative? We would say the max value, or the maximum value of the directional derivative at negative 2 comma 3 is del f of negative 2, 3, the magnitude of that, which is 4 square root of 61, which is this right here. Gradients and curves. Theorem 414. Suppose a function z of f of x comma y has continuous first-order partial derivatives and an open disk centered at a point of x naught comma y naught. If the gradient of f of x naught comma y naught does not equal 0, then the gradient of f of x naught comma y naught is normal to the vector curve of f at the point x comma y. Example 5. Find the function f of x comma y equals 2x squared minus 3xy plus 8y squared plus 2x minus 4y plus 4. Find the tangent vector to the level curve at point negative 2 comma 1. Okay, so we want the tangent vector. To find that tangent vector, we will have to, once we find the vector, reverse it and multiply it by 1. But we'll get to that at the end. But meanwhile, we can go ahead and find those partial derivatives. So we have f of x, or f of partial derivative terms of x and partial derivative terms of y. So for x, we get 4x minus 3y plus 2. For y, we get negative 3x plus 16y minus 4. All right, to write it as our gradient, we get 4x minus 3y plus 2I plus negative 3x plus 16y minus 4j. And we evaluate at that point. So we just plug those in so that we get del of f at negative 2, 1 is equal to 4 times negative 2 minus 3 times negative 1 plus 2I plus negative 3 times negative 2 plus 16 times 1 minus 4j. So that gives us negative 9I plus 18j. Now to obtain the tangent vector, it's like finding the opposite negative. So we obtain the tangent vector by reversing and multiplying by negative 1 the components. So our answer would be negative 18I plus 9j. So notice we swapped them and changed the signs. Next question, definition. Let w equal f of x, comma y, comma z be a function in 3 variables such that the partial derivative of x, partial derivative of y, and partial derivative of z exist. The vector del f of x, comma y is called the gradient of f as defined as, and just as before, ijk, but now we have a third partial derivative. So pretty straightforward, just as you have done. I'll leave this one for you. I think you can do this. So you find your partial derivatives, right, for each one. And then you find your gradient. So you'll have something I, something j, something k, which is the something is what you found above. All right, that's it for the section 4.6. I hope you enjoyed it. Thank you.